say it's a real pleasure to be here. I don't know if any of you have ever visited Texas A&M University. If you do, if you have, you know we're based in a town called College Station. And College Station is perennially confused with College Park. People always ask me what life is like in College Park. And until today, I could say I have no idea. I've never been to College Park. But now I can say that I have been to College Park. And your campus is quite like our campus, I must say. Yours is a little more suburban. I think we're out in the sticks. We're about an hour and a half from Houston and an hour and a half from Austin. And so driving to either of those major cities, you'll certainly see cows before you get to either of them. So not quite as suburban as yours. So I hope that my slides are not going to be too small, which will be a good lesson to me because I'm always telling my students, oh, the text that you put here is too small. We need larger, fewer bullet points with more things. And now I may discover that I've fallen into that trap myself. So yes, I would like to talk about task allocation methods for coordinated multi-robot systems, and I'm going to presume that not everyone in the audience necessarily knows a whole lot about robotics, and so I've kind of I'm going to try to attempt to talk about 4 different algorithms at a relatively high level, and then we can dive into a little more detail if there's particular interest in any of those. So let me try to talk about motivated task allocation methods in general. So here are 4 videos that you might see on YouTube. Perhaps you saw the TED Talk of Vijay Kumar's work with these quad rotors using Viacom motion tracking system, so that they have good pose estimates. Or perhaps this is an example of a European Union-funded project called Swarm Robot Systems. Most people are at least aware of this idea of robots playing soccer. What was it? I think now 18 months ago, the Kiva Incorporated was bought by Amazon, maybe 2 years ago, for $700 million. And their big technology is they have these robots that move things around in warehouses. So if you've ever seen any of the new warehouses that Amazon is building, they are truly massive structures. And that's because they have these robots that take care of the logistics of moving items from one place to another. Interestingly enough, they still employ human workers that they call pick workers who will take the items off the shelves and pack them into a box. So a human still is involved in putting your DVD or your book into the box and sending it to you. But they just put a query which says, fetch this item with this ISBN number and bring it to this pick worker, and the robots figure out how to do that. And each of these 4 systems involve some variation of what I call task allocation. Now, some of the people, in particular people who work on RoboCup, might not call that task allocation, they might call that role allocation. But essentially it boils down to the same thing. There's a question of, there's some work to be done by the robot team, by the robot system, and some number of robots, and you have to figure out which robot should do which piece of work. And that's what I'm considering the task allocation problem. None of these 4 are examples of robots from my lab, so let me give you an overview of the particular problem that motivated the 4 task allocation strategies I'm going to talk about today from my own work. And this was some DARPA-funded project called Landroids. And the idea was to have what they called agile robot teams. So the intention is to have people who are interested in, say, doing some reconnaissance in a building who don't have any wireless infrastructure. And the idea is to build little robots that you could then place into this environment. They could do interesting, useful things as robots. So they could, for example, map the environment. And then they could act as wireless relays for people who were navigating and trying to communicate. So these little robots were built by the hardware performer of this project, which was iRobot. They were called Ember, but they're now available in a slightly modified form as robots called first-look robots. But they're intended to be very small devices as opposed to the large platform system. And so the idea is that you have these robots that are dropped by what DARPA uses the term warfighters, so they're dismounted warfighters, and then they act as radio relays they act as radio relay nodes, and the idea is that they will autonomously move to maximize communication coverage. So the intention is that maybe you have 8 or 15 of these. In our overall demonstrations, I think we got system trials with as many as 12. So we're not talking about huge robot swarms, but we are talking about robots that were moving in an environment which is, not, I would consider, a benign environment. There would definitely be all sorts of interesting things that could happen. And so we were considering robots deployed across multiple floors. And initially, actually, the robots were very sensor impoverished. The main piece of information they had was their radio signal strength. So they would wander around, and they got a sense of how well they were performing the the background, the mesh network, on the basis of the signal strength that they were reading from, initially it was a single antenna, and then they could look at some routing quality statistics at the link layer. That was essentially all the information they had. And from that, we had to come up with a policy that got them to move around in a sensible way. So our team, as I said, there was a hardware team. Our team was working predominantly on software. And so we were interested in building a mesh network, so we had to deal with the question of how do you initialize that network, given that you have no real information about where the robots are. Then we want to try to optimize the topology. So once you've figured out more or less that you're in a room and there's some other robots you can talk to, the question is, can you move around in the room to try to improve the connectivity? So the problem there is that you're trying to overcome small-scale fading effects. So that's fairly difficult to predict. But one thing you can do is you could build a local map based on experience and use that to improve your performance. So that gives you optimization, which we kind of call smart wiggling, because you have to move on the order of half a wavelength to get, you could get as much as an order of magnitude improvement in signal strength. But then there's also a question of topology optimization. So that gives you a little local movement you can make, but it may be that you can look at the network itself and determine that this is a weak network in the sense that there is one node which is particularly critical, and if that node is eliminated or fails, then your network is going to be partitioned. So if it turns out that you have 10 robots and only 6 of them are needed to form a spanning tree, then you have 4 excess ones, and you can decide where to put those 4 ones. And it's a question of which is the best place to do that. And so we worked on that problem too. And we also worked on the question of self-healing. So that's the case where one robot has actually been eliminated, or 2 robots have been eliminated, and you have to go drive your additional robots into a place to patch those holes. And so, apart from network initialization, which is really this dilemma of not knowing anything at all about where you are in the world, the question of topology optimization and self-healing have elements that look like banding problems. So we had to develop initially some techniques to be able to distinguish line-of-sight connections from non-line-of-sight connections. And the way we did that was by the fact that
So self-healing is basically replacing the robot.
That's right. And well, there are different models. So if you destroy one robot, one thing you can try to do is to try to bring the other robots closer together. So it's not necessarily a replacement, but in our model we did look at a replacement case. Yes. And the reason we did that was because we could look at the network, and then we could determine if there was one which was, say, less important than any of the others. So we could determine that it was unnecessary on the spanning tree, remove that, and then use that as an excess one. So we treat it as an incremental redeployment problem. That's exactly what we did in self-healing. So we had to work on some pretty low-level antenna techniques, things that would distinguish line-of-sight connections from non-line-of-sight connections, just by looking at the fading statistics over time. But I would say the main thing which allowed us to achieve robustness is, of course, in a multi-robot system, you're interested in exploiting the fact that you have redundancy, you have multiple robots. And so the first thing was to think about anticipating failures and placing robots at crucial bridging points. And the second thing was to use low-level behaviors such as your signal strength and high-level behaviors such as deliberation and planning to figure out what to do. And today I want to talk about some of the algorithms we developed in this category of what I'm calling deliberation, so task allocation and search. And I want to talk about 4 improvements that we made over the state of the art for task allocation. So first, let me give you a formulation of what we mean by the task allocation problem. This is essentially a matching problem. So we think of it this way. We have some set of robots. So I've got, in this case, 3 colorful robots, and I've got some work. So I've got some logs that need transportation, some masonry that needs some work, and perhaps a robot that is going to operate a crane to build a house. And what I ask is, I ask each robot how good it is at performing a particular task. So give me a cost estimate. So robot 1, so let's say robot 1 is the green robot. I say, for each of these 3 tasks, how much will it cost you to perform that task? And I write that down in this cost matrix here. So I have a row for robot 1 for each of my tasks. And I do the same thing for robot 2 and the same thing for robot 3. And then what I ask is, can I make an assignment of robots to tasks? So that's to say, pick one element from each row and one element from each column. such that the sum of the costs is minimized. Okay, so I have some constraints there. I'm saying robots perform exactly one task, and tasks are performed by at most one robot. So that's the particular situation we're looking at. Now, there are certainly generalizations, and people have looked at them, but in our case, we had one robot, and we had one place in the network we wanted it to go, and so it was fairly natural to think of this as the problem of one robot, single robot task, single task robot. And in this case, we're also, although we're solving a problem over time, we're thinking about this as a separate planning instance. So we want to take an input matrix like this and come up with a solution, and we call that solution an assignment. And then we go and we execute that assignment. So if it turns out that, in this case, the minimum cost has robot 1 performing task 3, then if that's navigating somewhere, then the robot goes and figures out, based on, say, a motion plan, how to navigate those local lobs to the keyboard and takes care of all those low-level details. So that's why I consider this at the deliberation level, at the planning level. And I'm going to make some simplifying assumptions just for the presentation. So I'm assuming that the number of robots and the number of tasks are the same. That's not necessary at all. We can invent fictitious robots that don't do any work at all and so have a very high cost. And I can invent fictitious tasks if needed, so I can always get a balanced input problem. We're also considering information that's available at this instance in time. So I'm not asking you to estimate how good do you think you will be if over time you're going to discover more information. In fact, what we would like to do is come up with an efficient algorithm to solve this based on the information we have right now. And then later on, if new information becomes available, then what the robot does is it broadcasts, hey, I think I've changed my mind, let's replan and see if there's something new we should do. So if we can do this incrementally over time and efficiently, then we can kind of deal with this information staleness problem. And so that's the third one, so the solutions are periodically recomputed. Okay, so there are a bunch of challenges. So one thing is, we want these, as I've said, we want to do this repeatedly, so we would like to be able to do this matching problem quite efficiently. There are possible failures in the network, as I sort of gave in the Android overview. We can think that if we're going to aggregate all information potentially at one location, then it may be a dilemma if that robot is the robot that fails. So then we would have to we have to add some additional systems complexity to detect that no allocation has been made, and then elect a new robot to run the allocation and so on. In general, we want to minimize communication. We want our algorithms to be maximally flexible, so if new information becomes available, we can inject them into them, these sorts of things. So these are the general challenges that exist in this area, and there are different solutions that run the gamut from centralized solutions to distributed solutions. And I'm going to try to actually talk about some that are centralized, some that are distributed, and some that we have this property which we call local centralization, which is that we're able to sort of do something between centralization and distributed coordination. So it's kind of like electing a sub-captain, solving a sub-problem, and then aggregating those solutions. Okay, so let me talk about, there are 4 algorithms I'd like to talk about. So the first one that I'm going to give it's just going to be sort of an appetizer, but it's a problem. It's considering the assignment problem that we've looked at, and asks the question, how can we partition that and distribute that over robots? Then I'm going to go and talk about a task swap assignment algorithm, and that's the primary thing that I want to focus on today. But I will give you a sense of how we've thought about uncertainty and the interval Hungarian method we developed, and how we also do navigation through this matching graph, which is related to the Hungarian method. And so actually, the top 2 are really decentralized methods. Perhaps the task assignment method would be a truly distributed method, but they're definitely not centralized methods. Whereas the bottom 2 are generalizations of the so-called Hungarian method, which is a centralized method. Okay, so it seems like I've got them out of order. So in fact, let me take that back. My intention was to talk about partitioning first, but I swapped the order. So let's talk about task swap assignment algorithms first. So task swaps are a really intuitive idea, and they're an idea which is so intuitive that several people have invented it independently. And have to be reminded to go back and look at the literature and say, yes, this is a great idea, but you were not the first person to think of it. And the first person that I'm aware of is Sandholm, who studied this not in a robotics context, but in a multi-agent auctioning context, or what he calls contract net, I think in the mid-80s. And the idea is that if you want to match robots to tasks or workers to any amount of work, what you can do is you can just start with any initial assignment. It doesn't have to be an optimal assignment. Just say to each robot, just pick a task. And if you want to make sure that there are no conflicts, so you could, for example, say robot 1 pick task 1, robot 2 pick task 2, and so on. So you have a non-conflicting assignment, but it's not necessarily optimal in the sense that you're probably going to pay more cost than you would like to. And then the idea is, like I said, it's very simple. If robot 1 and robot 2 bump into each other and they're in communication range, which I've sort of indicated here, that's these two in this click here. They can look at each other and they can look at their relative cost for performing the task. So robot 2 is currently assigned to task 4 and it has a cost of 5, but if it could perform task 2, it would have only a cost of 3. And robot 1 has a current cost of 4, but if it were to do the other task, it would still only pay a cost of 4. So if we look at the sum, that suggests that just exchanging tasks between robot 1 and robot 2 would be a productive thing to do. And so what you can do is you can take, if we visualize this in the matrix, what we're looking at is we're looking at this element, which is the current assignment, and we look at the off element from that, and we compute that that's a worthwhile thing to do, and so they may choose to exchange tasks. And then robot 1 encounters robot 4, and they exchange tasks and so on. And the idea is it's very lightweight. All you have to do is wander around. When you see another robot, you say, hey, should we swap tasks? And if it looks like a good thing to do, then you go ahead and do that. Like I said, it's a very intuitive idea, and you can imagine implementing this very easily over UDP or something like this. So the dilemma is that one might ask, well, how well does this actually do? And it might be that you could say, well, there could be a bunch of tasks, individual pairwise swaps that seem to make progress, but don't actually get you to an actual optimal solution. In fact, there was a generalization proposed a little later, which said, well, maybe what we should do is we should think about trying to improve performance, and the way we'll improve performance is not by looking at single tasks, but task swaps, but by group task swaps. So just to give a summary of the algorithm, the swaps occur in a fully distributed way. Each robot is always holding a task, so they can always be performing some work, which in our case means, since we're looking at mobile robots, they're almost always navigating some way, which is handy because that also means you're likely to encounter a new robot and you could potentially swap. And any swap we perform must improve solution quality. But the drawback is that optimality is not guaranteed, and unfortunately swapping order and the partners that you encounter matters. And the trouble is that if you're not going to say anything at all about how robots encounter one another, it's difficult to analyze the number of swaps that will occur. So we made an observation, which is that some people have proposed in the literature that to generalize pairwise swaps, you could do a little better if when 3 of you got together, you formed a little clique, and looked in the clique and said, is there any arrangements of swaps we could do that which would improve the performance a little further? And you can then run that algorithm with varying click sizes and see how performance varies. And it turns out if you do that, as the clicks get larger, you get better and better, as you might expect. And at some point, of course, the clicks become the whole system, and essentially you're solving the overall matching problem. But what we haven't understood was the fact that there's essentially an optimization problem, which is going on here, which is we want to minimize the global cost. We want to minimize the sum of costs. But the constraint we have is, we have 2 constraints. One is that only one robot can be assigned to each task, and the other constraint is that each task should have at most one robot. And so there's 2 ways you might generally approach this optimization problem. The first might be to say, find me the thing with the cheapest, with lowest cost, and then I could steadily look at things with increasing cost until I find something which satisfies the constraints. Or I could go the other way, which is to start with things that satisfy those mutual exclusion constraints and try to drive the cost down. And what's going on in this case, is in the task swapping case, is we're doing the latter. We're starting with the scenario where the constraints are satisfied. We're maintaining the mutual exclusion constraints. Each robot always has a task assigned to it. And then there's this handoff protocol, and at that point, each robot still has one task associated with it. And so that operation can be understood in terms of a primal dual theory, as a primal operation. So the core operation we made here was that the algorithm leads to an optimization interpretation where the basic step is a primal operation on this primal problem. And then it turned out we went back and looked in the literature, and it seemed that people had looked at weighted matching problems, which is what the assignment problem is. And for a long time, the classic algorithms are all primal dual algorithms, all ones which operate in the dual interpretation. So the Hungarian algorithm, which we'll come to, is one example of that. But Bertsekis' auction algorithm, which is another famous algorithm, is an example of a primal algorithm, of a dual algorithm. And we found only one example of a primal algorithm, which is this Belansky-Gamora method from 1964. And then we thought, okay, well, we can look at this algorithm and see how that works. And we discovered that it had some properties when it was a primal method, which was attractive, but it didn't manage communication cost at all. In fact, it's an operations research piece of literature, so that we're not considering this in a distributed setting at all. And so we were able to come up with a swapping strategy, which is basically an improvement of that. So let me just sort of sketch how the algorithm works. We have a similar situation here. We've got robots on the left. Robot 1 is associated with task. Robot 3 is associated with task 1. Robot 1 is associated with task 2, and so on, shown in the matrix. Okay. So what we observe is that when there's a click, as I call it, a communication click, what we actually see is a structure in the matrix, which is of the form of a loop. So if you can see the animation there, what's happening is that we're proposing, if we're going to do a task exchange, the task from robot 1 is going to sort of move over, and then that's going to displace the task from robot 4, and that's going to displace the task from robot 2, and what ends up is we end up with a loop structure. Is there a question? Okay. And that can be interpreted literally as the robots forming a task exchange loop. Because they're handing tasks from one to each other. And so the question is, actually there are two questions which might arise. So the first one, which I had said, you can envision these swaps getting larger. One question is, how large do they need to be? So could you solve the problem with swaps of size 2 or size 3? And actually we were able to answer that question, and the answer is unfortunately not. If you give me a swap size of size k, I can construct a matrix and an ordering of swaps where you will not reach the optimal solution by any k size swap. On the other hand, that's a constructed matrix. So it may often be the case that when you're given a reasonable matrix, or just an actual task-based matrix, it turns out that it isn't this evil monster which forces you to do these very large task swaps. So how large these loops need to actually be in real life? And so we answer that question empirically. But let me just give you an idea of how we find these swaps. So, and sort of how we prove that the algorithm is on. So our strategy is quite simple, which is to look for swap loops of this structure. And the way we do that is essentially to construct a search tree in the space of swaps. So, and we employ a very simple strategy, which is essentially a breadth-first search from a particular robot in the task structure. So it will encounter some other robots, will look at the matrix, and start to expand a breadth-first search until it finds that there's a leaf in the tree, and this leaf could back up to itself, could be an exchange, and then that gives you a loop in the tree. But how do we know that this is optimal? How do we know that so the first thing we can argue is that, well, we can enumerate all of these swaps, but how do we know that actually we're solving the optimization problem optimally? It's one thing to say we can find, in some sense, good swaps. Well, it essentially depends on the primal dual theory of optimization. And so our idea, essentially, the rule of what is in the linear case, I guess known as the rule of, essentially the KKT conditions, but this notion of complementary slackness. So if you can find an input where both the primal and the dual are both feasible, then you've found an optimum. So we already said that the primal problem is maintained as feasible because every step in the algorithm involves a swap, and a swap maintains the feasible constraint. So what we show is that if you search the tree, eventually you end up with a solution which is a valid solution for the dual, and when the primal and the dual are both valid, then you have an optimal solution. So that's kind of how the proof proceeds. So, okay, so I'm going to skip over some of these details, but we can essentially find a solution which satisfies this constraint. And here is a form of a binary search tree. So basically what we do is we start with an individual robot, and instead of saying, oh, here's another robot that I should exchange tasks with, we say, well, let's look in the matrix of all the other robots that I could potentially exchange tasks with, and then do that at the next level, and do that at the next level, and do that at the next level, expanding the tree downwards. Now, we don't actually need to form, this is kind of a graphical representation. One can actually find these loops by doing a breadth-first search inside the matrix and doing some tricks so that you can get this down to n cubed log n. Now, the best algorithm that we're aware of to solve the matching problem is actually an n cubed running time, where n is one of the dimensions of the matrix. So, just to be clear, we're given n squared data as input, and this is an n cubed log n algorithm. Okay, so that's fairly similar to what is sort of the best centralized algorithm that's known, but as I'll say in a second, this algorithm has some interesting features. So for one thing, it has this interpretationist swap loop, so it's able to answer these questions as to how well do swap loop algorithms work. But it has this really nice feature, which is we can look at forming loops, finding the loops that we find, and then performing those exchanges only when we need to. So in particular, if I give you an input, and the input doesn't require k-swaps where the k's are very large. So if it takes as few as 3 robots or 4 robots to exchange this, then the algorithm will find loops of that size. So here's an animation. So we have a bunch of robots, the dark dots in the plane. Sorry, there's some tasks and robots. I think the robots are the dark dots, and the green ones are the tasks. And what we're doing here is constructing a matching by starting with an initial matching, and then detecting that some set of these robot task pairs should be exchanged. And what you're seeing here is a visualization of a loop that needs to be found. So there was a fairly large loop that was found, but it only involved, I think in this case, 5 robots. Okay, so what's happening here is as the search tree grows in size, we're involving more robots, and we're doing this dynamic. So the point is that if this algorithm, if a swap loop of size 5 is needed, we're only actually going to ever form a flick of size 5. It's never the case that we need to look at a larger. Okay, and so this algorithm actually has a few interesting properties. So one thing is that it allows, so I said it was related to Valinsky and Gamora's algorithm, but what it does is it focuses its computation on sub-portions of the matrix, okay, which is an idea that we're going to come to in the next algorithm we're going to talk about. So if you look at the number of entries visited, that's to say the number of cells looked at in this allocation matrix, while Valinsky and Gamora's primal method can explore a really large number as a function of stage. In fact, our algorithm is only looking at, in this case, of these data from those trials that we generated before, very few. So on the order of 10 entries in the matrix. It is.
So
yeah.
When you say decentralized algorithm, I guess you mean what we in computer science call distributed algorithm, right? So what I'm asking here is, the robot, every robot doesn't know the whole matrix. Right?
So this is, in fact, a centralized algorithm in this case, because every robot they communicate the whole matrix.
Communicate the whole matrix.
Yeah.
So they have access to the whole matrix.
So, yeah, so that's actually the conceptual visualization of this is that they know the whole matrix. In practice, they don't actually need to know the whole matrix, because what happens is that they have particular queries which are of the form, is there an element in this row less than this? So in fact, what you can do is you can keep your own row private to yourself, and then when you communicate with it, when you run the algorithm, if you can answer that query by saying, yes, I have this is task 3, then in fact you can do it without communicating the whole matrix. But that's actually why this first measure is meaningful, which is how many elements in the matrix.
Right.
But in general, So we solve this problem in a distributed, in a centralized way, which is to say we aggregate all the data somewhere, we compute on the matrix, and so on. But when we look at the optimization, so when we look at the complexity and the proof of convergence and so on, we consider that just in the centralized case. We're not thinking about the additional cost of messages exchanged just in the elements in a particular row. Yes, absolutely. And so if you look at the paper, in fact, there's a centralized variant and a decentralized variant for precisely this reason. Because in general, you would prefer not to have to communicate all these costs. In fact, I'm not going to talk about it today. In general, you would prefer to not have to compute these costs. What you would like to be able to do is to compute some costs and avoid the vast majority of them. So, let's see. Okay, so it has, as I said, the fastest algorithm we know is an n-cubed algorithm, which is kind of the line along the bottom. This is an n-cubed log n algorithm, so it does exhibit that performance practically. And then the original Walensky-Gamore primal algorithm, as you can see, is not an n-cubed log n algorithm at all. So there's some improvements over that too. But the part that we really like about this algorithm is that because you have an assignment at any point in time, if you stop running the algorithm before the minimal cost assignment is found, you still have a valid policy of work for robots to perform. So in that sense, it's an anytime algorithm, which is the initial phase of setting up the problem. But once you've executed that initial phase, if some swaps don't occur, that just means that you're going to incur more cost than you could have. And what's nice is that you can actually see, we only have these data, this claim I'm about to make empirically, but it has this nice linear performance profile. So you can get a notion not only of the fact that you can stop the computation early, but also how much cost you're going to pay for that. So you could infer when the additional computation is worthwhile incurring in order to reduce the costs. So you can kind of reason about the marginal benefit of computation. And there are other algorithms that involve performing sub-allocation problems. And one of the nice things about this algorithm is you could use it in place of other systems where you need a sub-allocation problem to be solved. So I'm actually going to give an example of that in the next section. Okay, so let's talk about partitioning and distributing the assignment problem, which is sort of the second of the four algorithms that I want to talk about. I'm not going to talk about this in as much detail, but suppose again you've got a bunch of robots in some locations and you want to dispatch them to some other target locations and minimize the sum of the travel cost in this case. So what we observe is that there is spatial locality in this problem. It's not the case that I'm likely to take robot 11, which happens to be the one which is furthest at the top, and assign it to a task way down below. Right? There's going to be some number of possible tasks that I'm going to perform, but it's probably not the full set. Okay? So the question is, can we subdivide this overall assignment problem into a set of independent subproblems and solve those, and where the solutions of the subproblems give an approximation. So what we're interested in here really is the question of very large scale assignment problems and whether we can scale these algorithms up. Whoops. Okay, and so this is a little bit like a clustering problem, but it's unlike a standard clustering problem in the sense that we have two types of clusters. There's the clustering which has to do with where the robots are located, and the clusters which have to do with where the tasks are located. And really they're actually related by cost. And so we're actually trying to cluster them in some cost space as opposed to cluster them in some geometric space. So it does have the form of a clustering problem, and although in the case of a dispatching problem that is easy to visualize, really we're not saying a whole lot about the form of the cost. So it could be that if you're doing a manipulation task, those costs can't be geometrically interpreted so easily. And so we're I just want to make it clear that we're partitioning in the cost space. Okay. So the idea is to try to simultaneously cluster both the robots and the tasks, and then once you have these clusters, distribute those sub-assignments, and then what we can do is we can monitor the purity of those sets over time to figure out whether we need to do a reassignment. So we're interested in trying to see if we can save work by not doing the full assignment, and then also if we have to do repeated assignments over time and things change, you can save work again by perhaps only having to recompute in a sub. And then we can apply this idea recursively. So we can have multiple levels of subdivision. So here's an example of a cost matrix. And the first observation now in sort of the matrix form, which is the same as the one that we have geometrically, is that not every element contributes equally. So what we might like to do is to sparsify the matrix. And it's quite surprising, in fact, if you look at actual data from this dispatch problem. You can remove as much as 80% of the data, which is exactly why you wouldn't want to compute them, because you're computing a lot of stuff which is not important in the optimization. And you still only incur an additional 5% in that overall cost. So that's good news for a large-scale system, because that means that you get away with a lot less data, right, and still do really well. So there's a way you can represent this matching problem as a matrix, as we've seen. There's a way you can represent it as a bipartite graph, which we'll see in a little more detail. But there's also a hypergraph representation. Now, a hypergraph is like a graph where edges connect more than a single vertex, than a pair of vertices. So you can have a hypergraph has an edge is not just an element of two, but it can be a subset of the graph, or a subset of the graph. So in general, an edge connects one vertex to another vertex. Sometimes we allow an edge to connect a vertex to itself. So we allow singleton sets or sets of two, but in a hypergraph representation, you can allow larger numbers. And it turns out that if you represent the problem as a hypergraph, then there are really good methods for partitioning those hypergraphs. And if you then look at those partitions on the hypergraphs back in the matrix form, then what you observe is that essentially you've taken an ordering in a particular partition, and that's the same thing as taking a row and a column and swapping them. Now, if you think about the problem formulation, if we label robots 1 to 5, swapping rows or columns doesn't change the meaning of the problem at all, right? And so, if we have this task constraint, which is one robot per task, one task per robot, then what we're saying is we want one element per row, one element per column. And if we're allowed to permute columns and rows, then that means we can get it into a diagonal form. So in a sort of group theoretic way, that means that there's a permutation that we can multiply the matrix by and get it into a diagonal form where it's dominated by the diagonal. And in the hypergraph formulation, there are very efficient techniques to find these diagonals, and they're predominantly developed for doing matrix multiplication. So if you can get a matrix to this point where it has a strong diagonal, then you can do multiplication more efficiently in a distributed setting. And so we're able to take a task allocation problem and use these tools in order to commute a sparse cost matrix and basically come up with an assignment. And these are approximation techniques, but they're quite efficient. Of course, if your matrix multiplication is going to be, let's say, naively n cubed, you need to spend less than n cubed work doing the partitioning to save the work. So they're usually about n log n running time, or n squared in some cases. So that works pretty well. And then what you can figure out is if you, let's see if I can give you an example of some data. If I can get all my elements along the diagonal, then what I can do is I can take one of those diagonal blocks, and then I can apply the algorithm again to see if I could repartition that block and get them even further along that diagonal. Or in that block, instead, I could apply one of the previous algorithms we've looked at. So the anytime timer algorithm, for example, can solve an optimal assignment in that little block. And the beauty of that is that, of course, only the robots in that particular partition are involved. So we're saving some communication there. And the nice thing is that once you've identified those blocks, only the robots in that block need to communicate to each other. And we call those communicate with each other. And those subleaders can monitor what's going on in their block. So I just want to show you an animation. Here we go. So we've got robots assigned to tasks. And you can see the block form of the matrix. But as the robots and the tasks move, so this is a pursuit evasion case, the robots and the tasks are going to move, and you're going to see they start off those outer two blocks nicely disambiguated, but as the two partitions kind of crash into each other, they begin to diffuse. And so we have an algorithm which kind of has a parameter to determine when they've diffused to the point where now they need to be repartitioned. But the nice thing is that only those two blocks are involved in this repartition. So it's an algorithm which scales really well in this case. Okay, so those are the first two that I said I was going to talk in a little more detail. I did them in that order, swap groups first and then partitioning the matrix. I want to just give a sketch in the last, it looks like I have maybe 7 more minutes or so, to talk about the interval Hungarian method and navigation as a 3D matching graph. And there are again examples of task allocation problems, or in this case, how we can generalize task allocation problems to solve slightly different problems. So the typical example of the representation is in the matrix form. And I had said that there's a hypergraph interpretation, but there's also a biograph. Right? So what I can do is for each row and each column, I can write that, I can make a vertex for tasks, a vertex for rows, and then I can add edges between them and weight the edges proportional to the cost associated with it. And then what I'm searching for is a matching in this graph. That's to say, every element in the biograph should have one edge highlighted. So in this case, I've highlighted the 3 red edges. And so task 1 should never have 2 edges leaving out of that, and the same thing with, say, any of the robot tasks. Right? So this is the same mutual exclusion constraint specified in this particular way. And the observation is that, so the classic algorithm for solving this is the Hungarian algorithm, this is the n-cubed algorithm. And it's an operations research algorithm, which was actually, Harold Kuhn is the person who developed this, and it was actually quite instrumental in the development of linear programming itself, because he went to Danzig to discuss this problem, and he and Danzig had a conversation, and that ultimately led to the formulation of the simplex method. So it's actually, it's an important, this matching problem which arises in task allocation is mathematically quite an important problem. And as I said, there are other methods. The Hungarian method is an example of a primal dual method. One of the first primal dual methods actually for solving something which can be cast as a linear problem. Okay, so I'm not going to care too much about the mathematical details in the interest of time. But the basic operation that the Hungarian method and many of these related algorithms, their so-called augmented path algorithms use, is that they start with a path in the bipartite graph. So here's the bipartite graph at the top there, or here's one here. And what they do is they look for a path in this, in much the same way as we did our breadth first search. And they try to find something which has the form of an unmatched edge, a matched edge, an unmatched edge, a matched edge, an unmatched edge. And then they perform a flip operation. So if it starts with an unmatched edge and an unmatched edge, and you flip them, which is to say you change matched ones to unmatched ones and unmatched ones to matched ones, then what you end up with is an additional matched edge in this operation. So that interpretation of that is distinct from what's going on in the swapping exchange. Initially, we had 2 robots assigned to tasks, and then when we perform this operation, we now have 3 robots assigned to tasks. Okay. And the trick is to try to keep some constraints on the edges that we consider in the search. So these edges which are called matched, which are the ones that are labeled red, but these edges that are candidate edges, these are ones that we could match, and not all edges can necessarily be matched initially. So we start off with a small graph, and gradually we add more edges that we can add to search for these augmentation paths. And that's essentially how they operate. So you start with a single edge, and then the single edge which is matched, and this matching gradually grows over time. Okay, so the basic operation that occurs here is this flip operation. And when you perform a flip operation, you can essentially look at the costs that are involved in making that flip. So you have to pay some additional cost, perhaps, to deal with to make a flip from one assignment to another assignment. And in so doing, one can reason not only about the value which is needed for that flip to be an appropriate thing, but the range of values for which there would be inappropriate. And that's the so-called interval Hungarian. This is the method that we've come up with. And so rather than just performing a matching on a single matrix, what we do is we perform a matching on a set of matrices at the same time. And this is appropriate because one thing we're interested in is the question of how robust a particular task allocation is to uncertainty. So uncertainty arises in the multi-robot system in many cases, but one classic example is localization uncertainty. So I have a robot that doesn't know exactly where it is in the world, and then it wanders around and it uses a particle filter or something like this to determine where it is. And at some point, maybe it converges and it has a very good estimate of its location. At this point, let's say it's trying to form a task allocation problem. And the dilemma is that although I said we have a matrix of costs, if you don't actually know where your location is, you never have a single deterministic cost or distribution of costs. And so a meaningful question is whether the assignment that you have is robust to this uncertainty in the costs. And so by actually going back to that original Hungarian method and essentially reasoning not about a single element of the matrix, not just about a single element of the matrix, but asking if this is the assignment for this matrix, which in this case inconveniently is a maximization problem, not a minimization problem, but this is a maximization formulation, which we call the utility matrix. What we observe is that the maximum matching has a 9, 8, and a 3, and there's some values for which that would continue to be the optimal assignment. So if the 7 in the upper left-hand side decreased, that wouldn't affect the optimal assignment because we're not choosing that task, so you can make that task increasingly worse and we're still not going to choose it, for example. So the element in the upper left-hand corner could be as bad as negative infinity, and it could be as large as a value of 8. Only when it exceeds 8 does this affect the actual optimal matching. And so we can do that for, again, each of these elements. And so the observation of the interval Hungarian method is that if you take the Hungarian method and get it to compute on intervals like this, so it can give you a notion of how robust the input is to a particular perturbation. And you can do that in n to the 4 time. Yes?
Yeah, so I think the example you gave with the number 7, it can decrease indefinitely or increase to 8. Does that assume that none of the other values are changing?
So it's a perturbational method under the assumption that everything else is remaining the value that's given right now. Yeah. Now there are some ways you can reason about the relationships between elements. But they're not so straightforward. I can put it that way. You can say, for example, conclude something about the values that the upper left-hand corner has to exceed. And so you can say, if those values come down, so suppose that some of the other values went down a unit, you can conclude that the value that would have to get up as large as 8 wouldn't have to go up as large as 8, it would only have to go up as large as 7, for example. We don't know how, you wouldn't have that much information about which values are going to change. So, but yeah, that's right. So it is a perturbation around the given input matrix, and by a single element, yes. Is that, yeah, okay. There's a second.
Okay, it's a close question. What kind of tasks can you solve with this? Are you assuming there's only constraints between pairwise constraints between tasks? So it's like some Markov assumption, first order Markov assumption.
Well,
Could there be more complicated tasks where you have relation with one task and the whole 2, 3, 4?
Yeah.
Okay.
So the tasks are presumed, their performance is presumed to be independent. So something like a dispatching task is a good one, where what you have is you have a box that is sitting in an office somewhere you want collected. And it doesn't matter which robot does it, but it doesn't help you to have 2 robots doing it. You just need 1 robot to go fetch that item.
Okay, so there's not equal constraint first order between this task has to happen before this task.
That's right.
Okay.
So it's only in some sense sort of mission determination as opposed to planning of sequences.
Okay. But you have a matrix, so.
Yeah, because so the matrix in this way is encoding a set of preferences over the.
Okay.
Yeah, that's right. So the interval Hungarian method runs in cube time. Sorry, the Hungarian method runs in n cube time. The sensitivity analysis using these interval runs in n to the power of 4, but it turns out you can distribute that. So in fact, if you run, so you take the centralized algorithm and you run it across each of your nodes, you can do that in n cube time. So in fact, you're actually able to get this down to n cube time, so you can get a sensitivity analysis for free, which is useful because a robot can determine. Well, let's show you some data. So here's an example of a robot in a building, and it's wandering around using a laser rangefinder, and it's communicating with other robots. It's just using a map. And let me see if I can show you the particles. So this is the map it has. And so it has, the environment is symmetric, so it's undetermined as to precisely which part of the environment it's in. And it's using this information to construct some notion of how certain it is about its cost. And if I do this with 3 robots over time, so let's see if the animation is in. And they're trying to do, in this case, just navigation tasks. So I have one robot that I want to be in the front of the building, and one robot that I want to be in the back of the building, say because I'm sensing something there. Then what they can do is they can figure out when the probability of, or when the likelihood, actually we do interpret it as a probability, but for a given robot, we say what is the probability that the costs fall within the range that the matrix predicts, and if it exceeds the threshold, then we decide that we're fine with that and we commit to performing that particular mission. If it turns out that the probability that that assignment is going to be wrong, and so therefore that will result in a perturbation of which robot should do which task, then the robots choose not to do anything, and they continue to wander around improving their information. So this has a particular advantage, which is that if you look at the overall successes, but also if you look at the number of times that a flip occurs, which is to say, if you take your estimate, you perform a matching, then you start executing the matching, and then you discover new information, and then you realize on the basis of new information that the matching needs to change. You get a swap. You do this over and over again. What you see is that actually, in the simple setting with 3 robots like this, you can have as many as 15 flips that could go back and forth on the basis of this. But if you use the interval Hungarian method, we're able to demonstrate. I think we got that down to 1 flip for us. So this, at a high level, is just another way to think about the problem of uncertainty in this matching graph formulation of the assignment problem. Okay, so I'm not going to talk a whole lot about this last problem, but the last problem is a question of if I've got robots deployed at particular target locations, and something changes, so I get now a new location, I'm performing self-healing, and there's a new place that I want a robot to go to, so new targets arrive, and new robots arrive. Where should the targets or which robot should go to which target? So I could, if I ignored the deployed robots, just assign these 2 robots to their targets, but I could also use the infrastructure of the existing robots to figure out how to do a routing through this network so that robots exchange tasks in this way. And it turns out that if you look at this in a matching graph formulation, then this encodes a matching graph like we've just seen, and you can do a search over this matching graph incrementally rather than from scratch. And so that allows you to solve that problem more efficiently. So let me just get to my summary slides since we're over time now. Okay. Whoops. Overshot. So I've tried to talk at different levels of detail on 4 different variations of the assignment problem. But the assignment problem is essentially a combinatorial optimization problem that arises in mission planning for groups of robots. And I've looked at 2, which are decentralized assignment methods. And the last portion spoke about this idea of a matching graph. And a matching graph is essentially based on a family of algorithms which came out of the Hungarian method. But all of these are centralized techniques which search over a bipartite graph. And I've sort of hoped that I've given you an idea of one way that we're thinking about trying to connect these techniques from optimization to fairly ad hoc techniques, the task swap techniques that people develop. We've started to think about how you could scale these techniques to large systems using partitioning and redistributing the design problem. How you could think about uncertainty in a particular way. And in the last sort of just animation, trying to give you an idea that you can also solve this problem incrementally, and that can save you some computation. Okay, so I'll stop there.
Yeah. So in one of the first examples of the swaps, in the beginning of your talk, the agents swapped tasks because it benefited the overall objective, the global objective function.
Yeah.
But I'm curious if you were instead to only compel agents to swap if it was better for each individual agent. The example you gave, it was better for one but neutral for the other.
Right.
But I suppose that it could get better for one and worse for the other, but still be better for global, the global objective. But what if instead you only compelled them to make swaps if it was better for them individually in a greedy way?
Yeah.
Would that still perform well? I mean, how would that work?
So I can try to give two answers to that question. I don't know that either of them will be particularly satisfying. So the first answer is that, well, if you're going to put the constraint that they both have to go up, then that means that there are fewer swaps that are going to occur. And so I would imagine that it's not going to perform as well at the global level as because all you said is that there's some set of swaps you can perform, and the set of swaps that you're considering under your setting is strictly smaller than the set of swaps otherwise. So my sense is that the suboptimality that you get with a swap method where the neighborhood is smaller is going to be larger. Now, I don't think anyone actually knows what the suboptimality gap there is. That would be a good question, but I would imagine that maybe the gap now doubles. But you could maybe turn that around and say, if we weren't looking at pairwise swaps, if we were looking at k-wise swaps, then it may be that your situation can also result in optimal solution, provided the k is larger, and there may be some relationship between the k's. It may be that if you 3 times the k allows greedy optimization versus not. The one thing to say is that although we're trying to find, say, the minimum swap, the minimum cost in the matrix, it is easy to construct a straightforward example where a greedy algorithm will fail. So just know that the batching problem is not a matroid. You can construct a case where if you pick, suppose we're maximizing. We have a matrix and we're maximizing. You can pick, you take the largest elements of the matrix and you select that. And now you cross out that row and cross out that column, and now you select the next largest, and you do that over and over again. Well, you can fool that algorithm pretty easily because you can have 101 and 99 and 99, and it's going to pick 100 plus 1 rather than, what is that, 181. So there are some ways you could trick it that way. So I don't know that anyone knows too much about formally about the performance of that sort of algorithm. But there is a separate set of task allocation algorithms. We've contributed one in this area, but I didn't talk about it. They're the so-called auction algorithms. So, and they go back to Bersekis' original algorithm he just called auction. Took the whole namespace of the first algorithm. But it's another example of a primal dual algorithm. So it explores both the dual representation. And the point is that there is, in that optimization, an interpretation of some of the labels that exist in other algorithms as profits. And there's an interpretation that it's as if you were running an auction. So you elect an auctioneer, and then robots bid on particular tasks, and then those tasks sell. And in that way, they behave greedily in a sense. But there's still the auctioneer who kind of oversees the auction and has to choose the prices in some way. And so there are ways that you can think about agents behaving optimally or greedily optimally, provided that there's some agent which is also acting in a way to balance their greediness. But how that would compare exactly to what you said as a swap loop problem, I don't know. I don't know the answer to that question. But it's an interesting question. Maybe another interesting, maybe there's a philosophical question there, which is also whether if we're going to build cooperative robots, we should think of them as competing, or whether we should think of them as cooperating in some way. Yeah, right. Because actually they are competing, even though I've called them cooperating, they're competing for bandwidth, they're competing for space when they move through a door, right? There's always these coordination costs. So that's actually one area of work that we've looked in, is that it's one thing to go and say, oh, I'm a robot here, that's my cost to do that task, that's my cost to do that task. But my cost to perform that task actually depends on what everyone else is going to do too. I mean, your GPS does a really poor job if it only plans how to get you to a particular location and doesn't consider the traffic, right? And so the question is, how can you also correct for those interference terms? But those interference terms, ultimately, we're solving a summation problem, right? We're saying, what's the minimum sum of costs? And when there's interference or synergy, that's not a cost. The problem is optimization is fundamentally nonlinear in that case. So that's an interesting question, but it's unclear how to have even a concise formulation of that problem right now. Yeah.
Let me follow up on Cornelia's question. Now suppose that you have every task is some sort of a sequence. You have to do this, and then you have to do that. And then also suppose that you have specialist robots. Like one robot is a good digger,
sure.
The other robot has an oven and it can analyze the chemical substances that are over, and so on and so forth. Do you think this framework could be adapted to deal with this case?
So some people have looked at this, and you can show that that can be cast as a job scheduling problem.
Job scheduling.
Yeah, and the dilemma is that that's, well, even the case of just sequencing is NP hard.
Right.
And so you could pursue that. I don't know whether you could ask questions about how the quality of the approximation is the real question there. But yeah, so you could think about sequences of tasks, or you could even think about a cost which is dependent on when you perform the task.
That's right.
Is another, maybe even simpler variation than that. And another thing you could think about is you could have a specialist robot. So another simpler model than that is maybe we don't think about sequencing. Maybe we think about there's some tasks to be performed that need to be performed right now. But this task is going to take two of us to do together. So we have to move a piano, and it makes more sense for one person to guide. Then you get another set of combinatorial constraints on top of this problem, and then that's also going to be hard. So this particular formulation that I'm looking at is kind of interesting because it seems like if you generalize it a little bit in any direction, the problem gets a lot harder. Yeah, and so that's kind of what we're in some sense exploring locally to see what problems we can solve without doing that. But there certainly are cases. I mean, picking up a table like this is a case where clearly one robot is not going to be able to do that. And so you get, the thing is you very easily get set cover type problems that arise out of these cases where you have to choose something where each robot is occupied somehow, but the sum of the costs is minimized. And so I don't know what the state-of-the-art approximation algorithms are for those problems. That's a good question. But it just turns out that in the problems we were looking at, self-healing, all these things, there were typically navigation problems that involved saying which robot should go to this location, or which robot should go to these sets of locations. And so they tended to fit this model reasonably well. But certainly manipulation tasks are instances where you get really interesting constraints now, and you can't think of it that way. Yeah.
Any more questions for the speaker? Okay, good. Thank you again.